Hello everyone, welcome to the class COT 5405 Design and Analysis of Algorithms. Today we will be covering the topic weak heaps. I am Shirendu Mishra and I am from the batch Fall 2022. Let's begin. The agenda for this video will be the properties of weak heaps, how the implementation of weak heaps work, and how the use of reverse bits is done in weak heaps, and how weak heaps can help in sorting. Before we deep dive in the weak heap concept, let's just quickly revisit the concept of heap. So a heap is a special tree-based data structure in which the tree is a complete binary tree. That's the main point here. And a few operations that heap data structure support is heapify, insertion, deletion, and peek. So the heapify process is in which we create a heap from the array. With respect to weak heap, we will dig deep into this later. Also, a heap can be of two types, max heap and min heap. As the name suggests, the max heap will have the root node as a maximum element, and it will grow from maximum element towards the lower elements, and the reverse is true for min heap, for which the node element will be the minimum. Let's take an example of max heap and min heap here. So if we see the min heap, the root node is 10 and it grows uh, beyond beyond 10 as we go in the lower levels towards 15, 30, then 40, 50, and respectively. Similarly here the max heap starts with 100, which is the maximum element. With the basics of heap covered, let's dig deep into the weak heap. So a weak heap is a data structure that is defined by relaxing the requirements of a regular heap. The regular heap, which we just discussed, will relax few of the requirements of that, and that in that way we will attain a weak heap. The structure of a weak heap is the same as a binary tree arrangement with some changes, which we will see later. And a weak heap is a single tree that can be imperfect but is still fairly balanced. Now we'll look into the properties of a weak heap. So it is a binary tree as mentioned earlier, and the properties are the root of a weak heap will have no subtree, so nothing at all on the left hand side of the root node. The second property is the value of any node is at least the value of any node in the right subtree. This can be a little bit confusing, but we will see an example later and that should make things clear. And the third property is quite simple, that nodes with fewer than two children other than the root will appear only at the bottom level or one level up from the bottom level. So with that said, let's look into how these properties are maintained. Also, just before getting into the example, we'll see the usage of weak heap. So weak heaps can be used for sorting and they are pretty good with that. And they are also used for implementing priority queues. Also, with respect to sorting, a weak heap uses a relaxed or a weakened version of the standard heap property for the sorting algorithm heap sort. So we already have a sorting algorithm with the help of heap in place. With the use of weak heap, we can do the same. Now, example of a weak heap. So you see the first point was that nothing will be on the left hand side of a root node. So everything towards the left of the root node 21 is blank. Similarly, one of the properties were that child nodes will only be missing for the bottom level or one level up from the bottom. So here that is also maintained. And the main property, the value of any node is at least the value of a node in its right subtree, which means that the right node cannot be smaller than the upcoming right node. So 21 towards 18, that's fine. 18 towards 10, again that's fine. And 10 towards 6, it's fine. The other way around is not true. So that is not a property. It can or it cannot happen. It's allowed. So if we go from 21 to 18, that is fine. 18 to 10 is fine, but 18 to 19, here we are moving ahead of 18, but that is allowed in a weak heap. So that is also one point to consider. In weak heaps, there is a very important concept of a grandparent. So, and the logic for the grandparent for a right node and for a left node is a bit different. So we'll see. Grandparent of a right node is immediate parent. So that's pretty straightforward for the right node. And grandparent of the left child or left node is grandparent of its own parent. So if you want to find a grandparent of any of the node which is on a left hand side, then you need to go to its own parent and then find the grandparent of the parent. Sounds very confusing, isn't it? But pictures speak better than words. So we'll see one of the example. The basic one, right. So if you see the point 1 here, grandparent of a right node is immediate parent. So right node 6 is because on the right hand side, so I've taken it as an example, and the grandparent of 6 is 10. So that's pretty obvious. Let's take the left hand side one, which is 14. So if you see here, this is a left node. So the grandparent will be the grandparent of the parent of 14. So parent of 14 is 19, grandparent of 19. Now again 19 is a left node. So grandparent of 19 will be the grandparent of its own parent. So its own parent is now 18. And now 18 happens to be a right node. And because right node's grandparent is its own parent, so we started with 14 and ended with a grandparent at 21, which is the root node. Another important part in weak heap can be merging of two weak heaps. So here we are seeing two weak heaps separate. One is 8 to 3, 6, 1, and then one is 9 to 4 and 2, 3. We'll try to merge these two together into a single heap. So the step 1 is compare the root nodes and separate the node which is maximum out of the two. So the two nodes are 8 and 9. Obviously 9 is greater than 8, so we'll take it out. So then this sub part will remain. So we need to work on this 4, 2, 3 part later, and this is as it is. We'll also work on 8, 3, 6, 1. So for now, as you can see, the weak heap 1 has been reduced. Weak heap 1 is as it is, but weak heap 2 has been reduced to 4, 2, 3, and 9 is now floating around. With this, now we will take the two remaining weak heaps and merge the entire weak heap which was unaltered to the node which was separated. Okay, so this 4, 2, 3 was separated out, so it will go to the left hand side, and clicked on wrong buttons. Yeah, and the unaltered one, which is 8361, will go towards the right hand side, and that's it. We have a weak heap which has merged the two, and the properties are satisfied. Let's quickly check. 9 towards 8, that's fine. 9 is greater than 8 towards 3, 3 is lesser than 8, and now 3 towards 1, so which means 3 is greater than 1, that's fine. So 9 to 8 to 3 to 1, and the left subtree of 9 is all blank, that is also satisfied, and the child nodes can only be missing for the two levels from bottom, so that is also satisfied here. So merging of weak heaps is a easy concept. Now we'll see the implementation of weak heap. So there are two types of implementation. One is a pointer based and one is array based. We'll work on the array based in this presentation. Before we move forward with the implementation, we'll just quickly see one of the weak heaps and how we will proceed. So I have written the uh, index at each node here. So 0, 1, then 2, 3, for this 4, 5, and then 6, 7. So this is the array base representation of one of the weak heaps. So 9 to 8, 5 to satisfied, and all the properties are satisfied. Okay, so this is how an array can represent. So after that, there's one more important point with respect to weak heaps, which is a reverse bit array. So we have array representation, which we have already done. From this we can fetch a reverse bit implementation Boolean array. So the Boolean array will have the same number of indices as we have in the original array, and then we'll see how we can populate the new array. The values inside, the values for any index can be either true or false. So let's see. So we'll start with 8. Okay, just as an example. So we'll see that what is the right child of 8. So right child of 8 is 5. According to array representation, that's correct. The right child of 8 is 5. So we'll put a false, which is a reverse bit. If the other way around happens, then we'll put a true. That's the only thing which we need to do here. Now for this presentation, this is the last topic, which is sorting with the help of weak heaps. So again, I've considered a very simple toy example here. Weak heap 8 to 6, and then to 0, 2, and 3. So obviously there are very few elements here, so 5 elements we need to sort. So I have created a blank array as an example. So first step is we'll be sorting the elements in the generic manner, smallest to lowest, and as we know, the weak heap will have its node value as the highest. So there is no there's no issue in pointing the last element of the array equal to the node value. So we are just transferring the 8 here, and we'll be left with 6, 2, 0, and 3. So this is what we are left with. But the point here to consider is that this representation, which is at the top, is not a weak heap. So we'll first need to convert it to a weak heap, and only then we can proceed with our array or sorting. So the conversion is pretty simple. The root node will remain as it is, and the highest value 3 towards 0 and 2. This will become a new weak heap. And again, as we have posted the node value towards the element of array here will post the new value, which is 6, towards here. So that's pretty clear, and we are left with 320. Again, 320 is not a weak heap. We'll convert it, and that is pretty evident. 3 towards 2 towards 0, that is a weak heap, and this 3 will come on here, and the remaining two values are already uh, following the weak heap property, and we can just put 0 and 2 to get the final sorted array. And that's it. We started with a weak heap, 8 towards 6 towards 2 3 and then 0 on the right hand side of 6, but in the end we got 0 2 3 6 8, which is sorted. So that's all for today, and I hope that you got to understand some concepts, at least some new concepts in this video. Thank you.